Section 3.1 is on page 204, and it talks about maximum and minimum values. This is where we're really going to start using calculus for multiple applications. So suppose I walk left to right, right? Let's say this is the point G, and let's say I walk left to right all throughout this. I'm trying to figure out what's happening. Well, let's see. If I walk left to right as I'm walking, do you see when I get to this point, I am at a peak? I'm going to call that B. And I start walking. And do you see when I hit this point, things will change? Instead of coming down, I'm going to start going up afterwards. And you're going up steady. And when you get to this point, the same thing happens. This point. So let's see how this works. I have all of these points. I'm walking left to right. As I walk from left to right, when I get to this point, if I look around by a small margin, a small tiny interval, do you see that I am at a peak? Meaning, if I move to the right, I'll be coming down. If I move to the left, I'll be coming down. If I am at a point and my only options are moving left and right, and in both cases I'll be coming down, we say this is a local maximum. So we have a local maximum at x equal, for now, b. That is, if I look at b by a small mark, obviously if I look ahead, I do know that's not the highest point. There's something above. But on this small hill, if you like, I am at a maximum. And as I continue walking, when I get to this point C, do you see if I move to the right, I'll be going up, and if I move to the left, I'll be going up? What do you think that's going to be called? That's a local minimum. So ever heard the expression, what's so good about being on the bottom? The only way from that point is up. There it is. How about if I get to point D? When I get to point D, I am standing right there, and I notice I am at a peak, right? If I move to the right, I'm going to be coming down. Move to the left, I'm going to be coming down. So D matches as well. E, that's again, move to the right, you're going up. Move to the left, you're going up. That makes it a minimum. F would be a local maximum. So local means only around that by a small interval. You know? That's either a maximum or a minimum. Now, we have an issue with A. Because I'm looking at A and I'm trying to figure out, okay, is that a minimum or a maximum? Since I do not know whether the left side look like this, that would be neither. Or the left side might look like this, that would be a minimum. So at A, I'm not sure. And at G, the same deal, I'm not sure. If this is to go back up, that's a minimum. But what if this graph continues? Wouldn't that make it neither? So, our definition of a minimum, if you move to the left or to the right, you'll be going up. And our definition of a maximum, if you move left or right, you'll be moving down. So if I look at this definition right there, definition 1, it says, I'm sorry, definition 2. I'm going to get to A1 in a minute. 2. It says, the number y, f of c, y. In our case here, f of b is the maximum. F of c is the minimum, local that is. F of d is the local maximum. And f of e is the local minimum. F of f is the local maximum. So, I said here local maximum at x equal b. But what is the maximum? It's the y value always. Whether the y is height, whether the y is weight, whatever it is. So, when I look at this definition, definition 2, it says we have a local maximum if the y value is bigger than all the other y's near or around this point C. In our case, we say we have a local maximum at B if all the y's around B are smaller than this y value. And vice versa. If you want to talk about a minimum, local minimum, you are at a local minimum if the y value is less than all the other y values around it. Meaning if you move to the left or to the right, you'll be moving upwards. So that's how this book is going to define local maximum, local minimum. As far as absolute maximum is kind of like the highest of them all. The y value is bigger than any other y all over the domain, and the absolute minimum y value is smaller than all of them. So local, I have to look at the left and the right, but absolute, I'm looking at all the y values. So if I'm looking at this graph and I say, you know what is the absolute minimum? Absolute minimum at x equal what? And absolute maximum at x equal what? So here you're looking at absolute minimum. You're looking at this, but this counts as well. So absolute includes the endpoints. Local doesn't, because you need to look to the left and to the right. So if I'm glancing at this, I notice x equal a would yield the absolute minimum. That's the lowest point anywhere I move along this, if this is the height. And the absolute maximum happened to be at D. This seems to be the highest point. So far so good? So we want to practice this a bit. And we want to look at page 211 and attempt to do this problem. This problem says, for each value A, B, so we have A, we have B, we have C, we have D, we have R, we have S. They say for each number state whether the function whose graph is shown has absolute maximum, absolute minimum, local maximum, local minimum, or neither a maximum nor a minimum. Well, let's get started. I'm looking for absolute. I'm looking at all the y values. This y value, this y value, this, and this. Do we agree that this is the highest of them all? Do we all see that? And wouldn't that be the absolute maximum? Do you also notice that it is a local maximum? Meaning around it. Do you see I am at a peak and there's only one way to go down? So there's only one absolute maximum in this case. And how about absolute minimum? Isn't this the lowest y value of them all? Isn't that the absolute minimum? But do you notice it's not a local minimum? So f of A is the absolute minimum, and f of R is the absolute maximum value. It happens at x equal each of these values. So this is where it happens, and that's what it is. Alright? How about f of B? Well, let's look at B and let's see if we can make sense out of it. If I'm standing at B, if I move to the left, wouldn't you be going down? How about if you move to the right? Don't you go down as well? That's the definition of a local maximum. So we're going by definition now. How about at C? If I look at C right there, if I'm right here, wouldn't f of C, do you see where it's included? It's included there, so you're standing there. Do you see to the right you'll be going down, but to the left you have to go up? Definition of a maximum, you move left or right, you'll be going down. Definition of a minimum, you move left or right, you'll be going up. Since on one end I go down, and on the other end I have to go up, that's neither. How about D? If I go to D, well, do you see at this point you'll be moving up no matter which way you go? That means f of D happens to be a local minimum. We did R already. And how about S? S, at this point, that I can't call a local, so it's neither. Endpoints are either absolute or neither. They can't be anything else. Alright, we're going to practice a bit more, doing a few more problems. Let's look at, so here they want us to sketch. Those graphs could vary drastically. There's no one graph fits all, but they should all share the same characteristics. Sketch a graph of a function from 1 to 5. We want the absolute maximum at 4. Now, it doesn't have to be positive. It could be here if you really want, but you have to draw everything accordingly. Let's say that's the absolute maximum. So what I have to do, I have to ensure that no other y value goes above that. And we have an absolute minimum at 5. At 5, I'm going to pick a point, let's say right there. Just make sure that no other y value between 1 and 5 will be below that. Of course, you could bring that lower if you wish. A local maximum at 2. At 2, I want a local maximum. Well, a local maximum looks something like this. So if I put it there, that's what a local maximum looks like. And I would like a local minimum at 3. At 3, I want to make sure that I don't go below that. And that's what a minimum looks like. So one possible scenario let me pick that's one possible scenario. Of course, there are many scenarios you could do. As long as this is the highest y value of them all, and this is the lowest y value of them all, you're okay. I'm looking at 12a. 12a says, alright, sketch us a graph, and let's see what they want here. Sketch us a graph of -1 to 2 that has an absolute maximum, but no local minimum. No local minimum. Okay, well, absolute maximum, no local minimum. So if I pick a point, let's say no local minimum, that means I don't want to include the left end point. I'm going to make that small, and since absolute maximum, I want to be up there, right? No local, so either I go straight up, or any one of those three will do. Alright? Now, they give us an equation. They want us to sketch a graph. Well, we're really good with graphs. This is a line starting at 2, rise 1 down, 3 to the right, and it's bigger than -2. If I throw a -2 in there, well, -1, -2. So that was at 2, right? 1 down, 1, 2, 3 to the right. If I sketch a graph of that, and that line is going to only be traced. Oh, come on. Okay, third time will be a charm. There it is. Something like that. And is the endpoint included? Yes, it is. They say here, sketch the graph of this, find the absolute maximum, local minimum. Okay, find the absolute and local maximum and minimums. Well, this, we have an absolute max of, actually, I could plug the -2 in, 2 1/3 at x equal -2. There it is. Okay, I'm going to stop here this video. I'll pick this up in the next video. I forgot to mention, there are no local extrema, meaning no local maximum, no local